now he will tell us about load balancing for every p-norm.
Thank you. So this is joint work with Aaron Bernstein, Seth Petty, Eli Proch, and Cliff Stein. Maybe I should mention that Aaron is no longer in Columbia. He's moved to Berlin, and I've just moved to Waterloo, so these are not exactly updated, but that doesn't really matter. Okay, so I'm going to start with a simpler problem than online matching that was mentioned here before, and that's a graph orientation problem. And in this problem, we're given an undirected graph, and we want to output a direction for each edge, a directed graph. And typically the goal over here is to minimize the maximum out degree. So we can see, for example, we have this graph over here that has these two centers and a bunch of leaves. And although the two centers have a fairly high degree, we can orient the graph so the out degree is a maximum 1. It's not too difficult to do. Okay, so there's not necessarily a relationship between, well, maybe there is, but you can sometimes orient things with a really low out degree, although the degrees are high. Okay, so this is related to the online bipartite matching problem, which I'll define here in terms that we'll use in this talk. So we have this bipartite graph. We have some clients on the left side and servers on the right side. That's one way of looking at it. And each client arrives online, and each time it arrives with a list of some of the servers. And the goal is to assign each client to one of the servers. It's a matching. Now what we have over here is that this assignment, once we make an assignment, let's say these are some assignments, each one of the clients is assigned to one server. These assignments are typically considered to be irrevocable. Once you make a decision and you assign a client to a server, you cannot change your mind. That's typically the model. And the usual goal is to minimize the maximum load. Okay, just like the graph orientation problem, where the goal is to minimize the maximum out degree, over here the goal is to minimize the maximum load. Okay, so this turns out to be a generalization of graph orientations, and the way to see this is that in the special case where each client comes with exactly two servers that it can be assigned to, then we can treat the servers as vertices, and each client is just an edge in between two vertices, and a match corresponds to an orientation. A match, if we match to this vertex over here, this server over here, it means that this edge is directed outwards, for example. Okay, something like that. Very simple. Okay, so I'm going to focus on the online bipartite matching for the rest of the talk, but we actually started looking at this problem from graph orientations, and it gives some nice intuition to what's going on, but apparently it fails when you're looking at some more complicated things. Some of the intuition that we had, which was a nice experience. Okay, so far what I've mentioned is people have looked a lot at the maximum out degree or maximum load, the infinite norm of the loads. And there's some tension between two objectives typically when we're looking at trying to load balance. So usually we're trying to minimize, there's some interest in maybe minimizing the maximum load, but also we want to kind of be fair with the distribution of loads. And minimizing the maximum load doesn't do that very well. So for example, if you look over here at this graph orientation problem, we have this clique over here of size 6 in the same graph with this star with 3 leaves, and this means that there has to be at least one vertex with out degree 3. No way around that. So the maximum load is going to be at least 3, which means that you could orient these 3 edges to leave the center. But that's not really fair for the center, because you could also orient these edges to go towards the center, and then these will just have a load of 1. So which is a little bit more fair. There's less of a load in a kind of fair sense. So typically, one of the ways of dealing with this is really considering the p-norm, trying to minimize the p-norm. So what's the p-norm, in case you don't know what that is? So we're going to focus on p larger than 1. So the p-norm is just this formula over here. We take this, if we have a vector with k coordinates, then we take all the coordinates, take them to the pth power, sum that up, and take the pth root. Right? I think everyone's seen this, right? So nothing to really spend time on. Okay, great.
They didn't let in the door people who didn't know this.
Okay, so all right, so I'm going to focus on minimizing the p-norm as opposed to minimizing the infinite norm, and this is kind of motivation as to why you might care about that. Okay, so the other thing we're going to do is, as I mentioned before, the decisions that we make, the models that people have considered, in these models, the decisions are irrevocable. Once we decide a match, we cannot change it. And it's easy to show that getting an order of 1 competitive solution is impossible with irrevocable decisions. You have an omega log n lower bound for many of the models, and then some models you can do a little bit better, but generally speaking, it's impossible. So one way around this is to give the algorithm more power, and the way we give the algorithm more power is by allowing the algorithm to reassign some of the matches. But on the other hand, we don't want too many reassignments to take place. Yes?
Does the competitive bound also apply to randomized algorithms?
I think not. So I should mention maybe I'm talking about deterministic algorithms. I think there's like a pi type of arguments. Yeah. Okay, so this isn't the first time this was considered. In the infinite norm case, this was already considered in a SOTA paper by Gupta, Kumar, and Stein, SOTA 2014. And roughly speaking, this is what they did. So there's a journal version that fixed a slight error over here, which was kind of crucial to understanding how these things work. There's a difference between the case where, let's say we somehow magically know a load upper bound for the optimal solution. Okay? So in the case where we know the load upper bound, we know a load upper bound for the optimal solution, then we can easily get a, let's say the optimal solution is k for the infinite norm, the low upper bound is k, then we can easily get a solution that uses only order of 1 amortized reassignments, and the max load is the most 2k. So given an upper bound for the optimal solution, we can get something which is the most twice the upper bound. Okay? And then given this, then they converted this solution to a solution that works for unknown load upper bounds, and the general technique is once you reach the upper bound, double things, rebuild everything works just fine. Okay, so this isn't too complicated. And you get an A-competitive algorithm with order 1 reassignments. This transition is fairly trivial. Okay? So we wanted to do the same thing for the p-norm, and we said, all right, let's try to figure out if we don't know a load. So we need to be a little bit careful what we mean over here by a load upper bound. So for each node, if we somehow know an upper bound on the load in the optimal solution for that specific node, right? Then for each node we have a different bound now, as opposed to the infinite norm case where we have the same bound for everything. Then we can still obtain a solution where the load on each node is at most twice its upper bound, right? So it's the same idea as in the infinite norm, just instead of having one bound for everything, we have different bounds for different nodes. Yes?
What do you mean by amortized reassignments?
The other way of looking around this is that the total number of reassignments is linear in the number of clients. Overall, the entire execution of the algorithm. Okay? So on average, it's constant per client. Okay? Right, and then we wanted to extend this to the case where we don't have load upper bounds. But this turns out to be really difficult. And let me try to explain to you what the challenge is. So for the infinite norm, given a solution for known loads, we can, as I said before, we can trivially extend this to the case of unknown loads. But it's not the case for the p-norm, and the reason is that the infinite norm case, what happens is that if we have an upper bound on the optimal solution, and now somehow this upper bound can be increased, it's being increased for the entire graph at the same time. But when we're talking about p-norms, then solution keeps changing more locally. Right? We can have this vector of different upper bounds, and then some of the upper bounds over here are increased, a small number of upper bounds over here are increased, but the rest stay the same. And this means that we don't have enough time to rebuild everything globally because it's only a local change. That's kind of the intuition as to why this fails. The solution for the infinite norm fails for the p-norm case. So we have to come up with something a little bit more complicated. Well, that wasn't the goal. The complication wasn't the goal, but that's what it turned out to be. So we have to come up with something a little bit different. And the rest of the talk, we'll try to give an overview of what we did. So first, I want to kind of touch on what an offline solution would be for this problem. And of course, we can always compute the offline solution for free in the background. We'll show that there is a polynomial time solution. And the ideal is that these solutions don't change much each time a new client arrives. So we have some vector of upper bounds of loads, and we don't want this to change too much each time a new client arrives. Okay? Then I'll show how to solve the known case, and I'll give an overview of how to solve the unknown upper bound case. Okay, so let's talk about the offline solution quickly. So what we do is, let's say this is a matching, then we're going to orient the edges. Matched edges are oriented from the right to the left. Unmatched edges are oriented from the left to the right. We're going to use augmenting paths. What's an augmenting path? Well, we can look over here. We start from 5. We take this directed path over here to something with load 1. Then we could flip this path, make this a matched edge, and the loads become closer to each other. Okay? As long as the distance, as the loads over here have a difference of at least 2. Okay? We can do this again over here between the 2 and the 0, and flip this entire path, and we get 1, 1, 1 over here. So we have a theorem that shows that if there is no augmenting path infinite only if the algorithm is optimal. This is true for any p-norm, for any p at the same time. There's one optimal solution. Well, sorry, an optimal solution for one. This gives optimal solutions for all p-norms at the same time. It's important to notice that it's kind of easy to keep track of opt as changes happen. So when you add a new client, you just attach it to one of its servers and fix augmenting paths. And if you noticed before, when you flip the path over here, the only loads that change are the first and last. Although you may have a lot of vertices in the middle, there aren't many, the loads over there don't change because they lose one and gain one at the same time. So the changes are kind of local. Okay, I should mention quickly that we have a simpler approximation for the optimal solution in an offline case for general graphs, for not the online matching case, but read the paper for that. So for the known upper bound case, what we do is the following. If we have an upper bound in S, we're going to create, if there's the upper bound is 3, then we'll create 3 copies of S and attach it to all of its neighbors over here. And the idea is that now we have, over here we're going to say that the max load is 1. Okay? So now we have an infinite norm case where the max load is 1, so we can solve this using the previous solutions, and this works for here as well. What's nice is that a match here has a direct correspondence to a match over here. There's a one-to-one correspondence. So that covers this case. This is fairly easy. A more complicated case is trying to take a solution for the known case and create from this a solution from the unknown case. All right, so this was a little bit more technically involved, and I'll try to give us kind of a sense of what happens. So what we're going to do is we're going to create a graph with infinite copies of each server. And infinite copies. Of course, we don't maintain infinite copies, but just the concept. The ith copy has capacity 2 to the I. And once the ith copy has been exhausted, we start using the I plus 1th copy. So let's say this copy has been exhausted because it already has one edge matched to it. We have 2 edges over here matched to S1, and now S2 is being used. This is currently the copy that's being used. So when a new client C arrives, we're going to add C to the graph, to this graph over here, but only add an edge to the last copy, the copy that's being used. Okay? And by doing this and using some combinatorial arguments, which are non-trivial, we can show that a solution over here gives a 2 competitive solution over here. And this solution now has capacities that are known because we defined these capacities, so we can use the known case to solve this case over here. Okay? And if you put everything together, then we get a competitive algorithm for opt. And in the paper, there's also some nice ideas of local sparseness notions for graphs, which I would be happy to speak about with anyone who's interested later on. Thank you.
We have time for questions or the next speakers. So, does this technique generalize to handle any other norms? This reduction that you mentioned, like even a weighted out norm or something like that?
No, it doesn't work for weighted. We looked at that. You might be able to do it with some work, but we couldn't see immediately how to do that. We didn't really think about anything else, so Log X. No, this has to. The X log X it would work. Anything with speed greater or equal to 1 actually would work. As long as it's convexity. Yeah. Thank you.